Okay, let's get started again. Let's see. Any questions about the homework that didn't get asked yet on Campus Prior homework due on Thursday? Yes.
What's the factorial function instead?
There isn't one. You just pass it to gamma or log gamma, as the case may be, with x plus 1. So as it said on the homework, gamma x plus 1 is equal to x factorial for x is an integer. And so, but more importantly, log gamma is equal to the sum of the logarithms of x, or I, from I equal to x. And so this is the one that we tend to evaluate. But anyway, yeah, that's the reason why there's no factorial function in Stan, although there probably should be, is that the gamma function is a generalization of it. So you can put x as a non-integer and gamma will work fine. But if x is an integer, you just get back to factorial as long as you bump it up by 1. And this is the reason why the weird thing that 0 factorial is defined to be 1. Like that was always one of the things that seemed like disconcerting in elementary school or whatever. But the gamma function evaluated at 0 is 1, which is why 0 factorial is 1. Other questions? So a number of people came to office hours and have been posting on Campus Wire. And I've got a lot of questions, which are fine. Maybe could have been asked earlier. But a lot of the questions are just still on like, what is the definition of this? Or this function, it's a mapping from what space to what space? Or like, what size is this thing? If you have those questions, you should definitely ask as soon as you have them. But those are questions, they're sort of like, well, a lot of questions are factual, but these are like very factual questions. And so these are things that you can get if you just put in more repetition and studying and like make yourself flashcards or whatever it is you need to do to sort of, you know, okay, understand what a prior predictive distribution is. It has a very technically defined sense. It differs from like one model to another, but sort of in general, like the answer to that question is readily answerable. If you need it answered again, ask. But the main thing is just keep practicing, keep reviewing with these concepts, you know, going over the old slides and the readings and what have you until, you know, more of this stuff starts to sink in. Anyway, okay. So today we're going to be talking about model comparison. And in order to do that, we first have to disclose the fact that we have an apparent conflict of interest due to using Stan outside of Columbia when Columbia is in the business of obtaining grants in order to develop Stan further. Okay, so we're talking a good bit about sort of the Bayesian perspective on things, Bayesian view of probability, contrasting it with the frequentist view of probability, which most of you, if you've taken a class that was either in the statistics department somewhere or a class outside, but sort of took the statistics perspective, a lot of times those would be taught, or at least historically, those would also always be taught from a frequentist perspective. And so we've had a number of contrasts between what the frequentist perspective on things is and what the Bayesian perspective on those. And we'll talk about those again. But just sort of bear in mind that a lot of things that people do when they're doing or using frequentist estimators, they think they're doing a Bayesian analysis in terms of the perspective on probability, the probability statements that you make about the conclusions, etc. What is weird and what they get wrong when a lot of people try to do a frequentist analysis is forgetting the frequentist definition of probability. So the proportion of times that something happens, and the limit as the number of repetitions goes to infinity. So one way to better understand frequentist thing, every time they say probability or have something involving probability, just substitute in your mind the proportion of times that something happens in the limit as the number of repetitions somehow goes to infinity. And so you just need to figure out what that something is and what is the thing that they're imagining being done over and over and over again in order to induce distribution of the thing in the numerator of the conception of probability. Anyway, there's another approach that you would have been exposed to last semester. Those were in the data mining class or more courses that are offered these days in computer science or engineering things, or just if you like do something online with data camp or whatever, tend to take more of a supervised learning approach. And we want to talk about how that contrasts with the Bayesian approach. So if we go back to something that I said on the first day, and I think at least once since then, we have 4 basic types of uncertainty that we want to acknowledge, or at least try to handle as best we can. One, uncertainty, what are the parameters in a model that we set up? So if we do like a regression model of some sort, it has coefficients, it has an intercept, it has, those are the main ones. It may have some other things, error, standard deviations, and whatnot. But we don't know the values of those. And so we, anytime we estimate a model, we conceptually speaking have uncertainty about those. Second type of uncertainty, what model should I be using, or what set of models should I be using? All the stuff that like the frequentist perspective, whatever its merits may be, are assuming you're estimating the correct model. So the distribution of p-values being, of some statistic being uniform or whatever, that's assuming you're estimating the correct model. But you should have uncertainty as to whether this or that model would be more appropriate for your situation. Indeed, that's really like the core debate in a lot of journals and stuff, different subfields, different, what is the best theory, what is the most appropriate theory, what's the most appropriate model that goes with the theory for some, phenomenon of interest, like why do people vote? Different models have been proposed to explain that sort of thing. And so a big question becomes, what model is best? Third source of uncertainty, what to do with the results, assuming you've estimated like the best model and now have obtained some parameters. What do you do with it? How do you go about using that to make a decision? And the Bayesian approach, it handles the other sources of uncertainty well as well, but it really shines in this third area because there's a very well justified path for taking estimates, of the posterior distribution and making a decision. So take that posterior distribution, feed it into your utility function. There may be some predictions or something involved in between. Anyway, evaluate your prediction distribution, choose the decision that maximizes your expected utility. It's a fairly simple process, although you do need to specify your utility function as to what you think is good and what you think is bad and how it different gradients in between, etc. Other approaches is murky at best, how you go from like the results of the quantitative estimation process to a decision or a conclusion or an action or something like that. And then the fourth source of uncertainty, did your software do what it was advertised to do? That's often not the case when you're sort of pushing the envelope as to what the model is. With Stan, it either does or it will tell you warnings and whatnot that things are not going well. And so that is a good aspect of this. But anyway, the main thing about supervised learning or machine learning, data mining sort of thing is very concerned with the decision to use one model as opposed to another. And they may be estimating like hundreds of different models or training hundreds of different models the way they say it. So supervised learning, you can think of it as a branch of quantitative methods that puts almost all the emphasis on the second source of uncertainty and to the not putting very much concern about the first or the third. And I mean, they try to do as best they can with the fourth. But in particular, they're de-emphasizing the first source of uncertainty, the uncertainty about the parameters in the model. They just take their sort of point estimate of that and go with it as if they were sure that was the truth, when really that, in no way should be the case. But in fairness, a lot of this stuff that comes out of the more computer science or engineering literatures is intended or envisioned to be used in data sets that are quite large. And if so, the amount of uncertainty you have in the parameters, if you're estimating the right model the right way, although it's not zero, it might be kind of negligible. For example, like when we estimated the diamonds model or like the wages one that you have on the homework, etc. We have tens of thousands of observations, which would be considered small by people who toss around like buzzwords like big data today. But with 50,000 observations on diamonds, you can get very precise estimates of the parameters. And so in maybe the cases in which the people who promote these methods are primarily thinking about them is in situations in which the estimated uncertainty of the parameters is pretty negligible. And the dominant source of uncertainty that you really have to worry about is, am I estimating the right model? Or if the right model is among the hundreds that I estimate. And so if that's your main worry, concern, am I estimating the right model? They have a now very well established procedure for addressing that question, and that is to split the data that you have into a so-called training data set and a testing data set, often putting like 3/4 into training and 1/4 into testing, although it doesn't have to be those exact percentages. And then you solve some optimization problem that defines your quantitative methods using the data from the training subset only in order to get those estimates of the parameters. And then you plug in those estimates of the parameters into your prediction function, predicting the outcome in the testing data. And then you evaluate some other loss function to see how well your model is predicting in the testing data the outcomes, and using that sort of predictive score measure in order to say that one model is better than all the rest, and then going with that one as far as using it for whatever you want to use it for. And after that, it gets a little bit murky in my opinion. But the procedure of splitting up the data, only using the training data to estimate the parameters, hopefully you still have enough training data to estimate those parameters with negligible uncertainty, then predict using those point estimates into the testing data with the testing predictors, see how well it predicts the outcome in the testing data, and then evaluate the different candidate models you're considering as to how well they do predicting the outcome in the same testing set. And that is really the essence of the supervised learning approach to what supervised learning people consider to be the primary question that they have to wrestle with, which is which model to use more so than the other three sources of uncertainty. So some of you were in the class last semester and have heard it before, but in which case you should have already known what I just said. But for those of you who maybe haven't, or really anyone, questions about just sort of the basics of this splitting into training and testing and supervised learning approach? Okay, so how does that relate to Bayesian approach and stuff like that? So the misfit function that is often being used in supervised learning, like sum of squared errors, or if it's a classification problem, like the log of the probability of success, those are almost always proportional to some log likelihood function. So if it's, sum of squared errors, that is proportional to the logarithm of a Gaussian log likelihood. If you're doing log probability of success, that is proportional to the likelihood of a Bernoulli model, etc. So these functions that are using to quantify misfit between a model and an outcome are essentially log likelihood functions, or exactly log likelihood functions, maybe multiplied by -1 because they tend to do minimization, whereas frequentists tend to do maximization, but that's not an essential difference. But what is an essential difference is that the supervised learning people will often add a penalization term on the coefficients of a model to the extent that they are different from 0. And the actual function they're minimizing is the sum of the misfit function and the penalization function. And so you might say, well, why would you be penalizing these coefficients to the extent they're different from 0 if you didn't sort of come into it thinking, well, most coefficients tend to be pretty close to 0. And that sounds an awful lot like a prior. And indeed, I would say almost all the people in the supervised learning accept the Bayesian view of probability and reject the frequentist view of probability in terms of degree of belief. And so the sum of the misfit component and the penalization component being minimized in a supervised learning context is usually going to correspond to the posterior log kernel for some choice of likelihood and some choice of prior. But the choice of prior is often really weird. So you'll see sometimes people in the supervised learning saying, well, if you look at things like this way and that, it has sort of like a Bayesian rationalization to what I'm doing, even though like no actual Bayesian would do that, even though you could. And by that, I mean, you could specify this sort of weird prior in order to make the function being minimized by the supervised learning people be a posterior log kernel for some prior. It's just, does that prior make a whole lot of sense? And here we have a table. There was in a recently published paper by Sarah Van Erp and 2 of her colleagues. It was supposed to pop up the citation. But anyway, you can click on the link to see the preprint of that, saying for these things which are like often referred to in supervised learning, like ridge regression or lasso or elastic net, these sorts of things, what is the prior whose logarithm corresponds to the penalty function being used by the supervised learning and has a reference to where that was sort of originally worked out. And so you can reinterpret what a lot of supervised learning things are doing as finding the posterior mode for a posterior that's defined by a log likelihood and a weird prior function being used as the penalization, or weird prior distribution, the logarithm of that being used as the penalty function. And so finding this posterior mode, not finding the whole posterior distribution, but then just sort of getting this posterior mode and then going with it in terms of making predictions going forward. So this might be a little bit easier to see in the context of the most common, or at least a few years ago, most common supervised learning method, lasso, which is going to minimize the sum of squared residuals plus this lambda term multiplied by the sum of the absolute values of the coefficients. And this is proportional to the negative of a posterior log kernel with a fixed standard deviation of 1, Gaussian likelihood, and what's known as Laplace priors on the coefficients, independent with a location parameter of 0, and some inverse scale parameter that is fixed, denoted as lambda. And if you sort of find the maximum or the minimum of that function, that is going to correspond to a posterior mode of a posterior that's defined by a Gaussian likelihood and this set of Laplace priors on the coefficients. And for the most part, people who are doing lasso are not really interested in anything frequentist like standard errors or confidence intervals or p-values or anything like that. Relatively recently, the Tib Shiranis, or two of them, Rob and his son Ryan, did something a little bit more frequentist, deriving the sampling distribution of the lasso estimator, but that was only in the past couple of years. People have been using lasso and just sort of not worrying at all about the standard errors and things like that. And I think that is kind of an interesting phenomenon, and an interesting phenomenon more broadly than just lasso, but with supervised learning in general, and is, you know, relationship to frequentist statistics since the days of Fisher, in which for most of that, you know, period, you could get like a graduate degree, maybe even a PhD in statistics, but not ever really be exposed to actual data. All you did for your like PhD dissertation was derive the asymptotic distribution of some new estimator and like show that it's asymptotically normal across data sets. And these people would get graduate degrees in statistics in other areas and be completely unhireable in the real world, because no one in the real world cares about the asymptotic distribution of whatever you derived across data sets. Companies like Google or Facebook or a bunch of other companies that are sort of in the technology sector, really, you know, they adopt the Bayesian perspective. They're answering questions like, what is the probability somebody will click on this thing? Can you predict me that? And, you know, all these people who would get graduate degrees in statistics had no idea how to do that. They just knew how to derive the distribution of an estimator across data sets that would do something like that. But they really only had one data set, even though it was giant. And we're not interested at all about the properties of some distribution, of an estimator across data sets. And as a result, these technology companies have given billions of dollars to universities to fund, you know, data science or sort of alternative statistics programs where traditional frequentist statistic concepts like, you know, hypothesis testing and confidence intervals and things like that are being de-emphasized in favor of things that are more useful and marketable to people who might want to hire, you know, graduates like that. Like, can you write code? You know, can you, you know, script your process for handling data, being reproducible, these sorts of things. But when you get, you know, down to the estimator, really just sort of only caring about the predictions, not caring really about the distribution of the slopes or anything like that. And I, you know, you can argue for or against things like that. There's a lot of like old guys in statistics. If you talk to them, they grumble that, you know, what data science is doing is just like what statistics has been doing for decades. But really what, you know, these machine learning people, they're doing a lot less. And it's being found to be more valuable in the real world. So what that makes you sort of question, you know, what is the value of all these things that people have been trained to do for so long in terms of p-values and testing hypotheses and confidence intervals and all that? What does it say about the sort of, you know, volumes of journals that have been published over the years where that was their sort of criteria for whether something could be, you know, published or not? You know, those sorts of things. So this has kind of been in the process of reevaluation. But in order to sort of bring out this contrast, between the Bayesian approach and the supervised learning approach. I've sort of drawn three things here. This is for a logit model that has just one slope coefficient. I've set the intercept to 0, and so I'm able to do like numerical integration in order to get the denominator of Bayes' rule. So the black line here is the Laplace Prior, or the L1 norm, as it's referred to in machine learning. Depends on the absolute value of the coefficient being input into it, and it has a mode where it's actually not differentiable at the mode, but its highest value is at 0. Okay. In the Bayesian context, that would be our log prior. In the supervised learning, that's your penalization function. And then we have the likelihood function of beta in red here. This is an asymmetric thing. It's kind of flat because I didn't have that many data points at the top. But anyway, the maximum likelihood estimator would be something maybe slightly less than 2. Oh, Sandhya, you had a question? You get penalized wherever the line is, wherever the black line is. So if you put in beta of 1, you get a penalization of like this, except in supervised learning, they multiply it by -1. So it's like worse. But anyway, if you're at 0, then you get the least penalization, which is to say no penalization. Anyway, the mode of the prior is at 0. The mode of the likelihood function is a little bit less than 2. And so if we were to take the frequentist perspective, we would estimate this coefficient to be like 1.9 something or whatever. And we could derive the distribution of that estimator across data sets that were randomly sampled from the same population as this one was, which was just simulated random numbers on my computer. So the frequentist estimate would be like 2. The penalized estimate, so the posterior kernel is in blue here. This is normalized to have an area of 1 underneath it. But the machine learning people would just find the mode of the blue line, which is the sum of the log likelihood and the penalty function. And the mode of that is also right near, it is 0 in this case, which is an example of a case where lasso shrinks the coefficient estimate all the way to exactly 0. And that's a large part in consequence due to the non-differentiability of the L1 penalty function at 0. But anyway, if we take the Bayesian perspective, this entire blue line is the posterior PDF. I've normalized it. It has an area of 1. And so where the frequentist would say, okay, our maximum likelihood estimate is close to 2. Let's just go with it in terms of like testing a null hypothesis of that it's 0 or something like that. Whereas the machine learning people would optimize this thing and say, okay, the optimum occurs when this coefficient is exactly 0. Let's go with that for the purpose of making predictions. Whereas the Bayesian would say, well, you've got the whole blue curve here that defines the posterior PDF. Every like little space of the subspace of the parameter space has some probability that's defined by this posterior PDF. So yeah, the posterior mode is at 0, but the posterior mean is not 0. Posterior mean is probably going to be some number between like 0 and 1. The posterior median is not 0. That's going to be some positive number. The posterior distribution in general is not very concentrated at 0. We have a whole lot of uncertainty as to what the slope is, but there's more probability that it's positive than there is that it's negative. So, if we integrate the blue curve up to here, that's the probability that it's negative. And if we integrate the blue curve from here, like all the way out to infinity, that's the probability it's positive. There's way more probability that it's positive than negative. So really, I like this example because we get 3 contrasting views of like what the answer is. The frequentist one that it's like a little bit less than 2, the supervised learning one that it's 0, neither of which has any acknowledgement of the uncertainty in this thing, which there's a ton of because I had like 9 data points. But the posterior PDF, the blue curve here, adequately reflects that uncertainty. It has a mode of 0 in this case, but neither the median nor the mode nor anything interesting about this posterior PDF is exactly 0. And really the real important thing is we have a lot of uncertainty, but the odds are tilted that this is positive compared that it's negative. But this was choosing a rather weird prior in order to make my posterior kernel align with the negative of the function being minimized by lasso, which might not have actually reflected really my true beliefs about what this coefficient is. And if I put in my real beliefs, I would have gotten a different posterior PDF there. Any questions about these 3? So, manner of speaking, historically, the machine learning, supervised learning approach is fairly hostile toward the frequentist tradition. They basically said, everything that you've been doing for the past 75, 100 years is useless in the real world. And we're going to do it our own way. And we're not going to care any at all about standard errors or confidence intervals or p-values or the asymptotic distribution of data sets we don't have or any of that stuff. And so you might say, well, if they are as hostile to frequentists as they are, then they have more natural allies with Bayesians who are hostile toward the frequentists for the same reasons, or a lot of the same reasons. But there's actually not that strong an alliance between the supervised learning people and the Bayesian people. The supervised learning, when they develop some new algorithm or something like that, say, well, if you look at things this way, it kind of has like a Bayesian interpretation. But the fundamental thing that sort of distinguishes real Bayesians is that you want to get the whole posterior distribution, not just some mode. Because the whole posterior distribution reflects your uncertainty in your beliefs about these parameters. And if you just find one number and stop, then you're not in any way capturing that uncertainty and not propagating it through to the decisions that you have to make, not acknowledging the fact that if you put a distribution into some nonlinear utility function or nonlinear prediction function, the distribution that comes out is going to be way different from the distribution that comes in. And there's no way you can sort of ascertain what the distribution that's going to come out if you just put in the mode. You have to put in the whole distribution and see what it looks like when it comes out the other side. And that's really what the Bayesian approach is. And with a lot of supervised learning people, they just yeah, we sort of define a posterior kernel, but we're not going to do MCMC to get draws to the posterior distribution because that takes too long or is too much work or whatever. So we're just going to use optimization, which we already have a library to do in Python or R or whatever. And we're just going to go to the top of this blue curve and stop. And then go with 0 as our estimate, as if we were sure, when there's no way we should be sure about anything. Yes, John.
The posterior, there are a bunch of people who teach and do research, and one of the founders of Coursera, Keller, she does, or is an expert in probabilistic graphs, largely in the domain of Bayesian analysis. So that's part of machine learning as well, isn't it?
Yeah. So
and she follows essentially Bayesian.
Yeah. So I'd say there's a lot of supervised learning people, Rob Tibshirani and others who say they adopt the Bayesian view of probability. They understand the penalty functions kind of correspond to priors. Why would you penalize the coefficients to the extent they're not 0 if you didn't think they were zero before you saw the data. And, you know, maybe sort of define even a posterior distribution when they sort of write it up in their paper. But in terms of what, in my mind, sort of distinguishes, you know, Bayesian from machine learning, or from Bayesian machine learning, which is like a class that you can take in the engineering school, is do you draw or otherwise analytically get the posterior distribution in your analysis? Or do you sort of like write down the posterior distribution and then do some other shortcutty thing to get a point estimate of the thing that doesn't have any reflection of your uncertainty? So there are some people who call themselves like machine learning supervised learning who do MCMC, and I would just call them like Bayesian. But there's a like larger group of people that sort of accepts the Bayesian probability, like writes down a posterior distribution, but doesn't actually draw from it. And those people I would only consider like quasi-Bayesian at best, because they're not really embracing the uncertainty and propagating all that through. So that to me is the main distinction there.
The other thing I wanted to mention was that split between classical frequentist and Bayesian that you are alluding to basically comes out of, from what I remember, like Yahoo and Google and so on, they were interested in huge data sets. So there are proponents that say, as long as you have a huge amount of data, nothing, no statistics or nothing that we do here in this class or in this university in the statistics department, that doesn't matter.
Yeah.
Because we have enough data and we can train whatever models we want. So that's the bend, that's the collateral damage, if I could put it that way, towards the frequentist school.
Yeah, so Hal Varian said something along those lines. He works at Google, but he used to have an academic position. Said something along those lines. It basically amounts to the first source of uncertainty that I was talking about. Uncertainty about the parameters is just negligible with the size of data sets that we have. And that is somewhat true for like Facebook size, Google size things. For social science, it's often still like not that true yet, even if you're working with like census data. But so in some contexts, yes, that is. But you still have the other three sources of uncertainty that I think a lot of frequentist and supervised learning approaches are not as attuned to dealing with as the Bayesian approach. And another sort of, I understand what Hal Varian is saying and other people who say things like that, but I would counter with it that when you have what seems to you to be a huge data set, you have an opportunity to really do a rich model on that. And so the bigger the data set is, the more heterogeneity there's going to be in the data generating process. And so the data sets that Facebook and whatever are huge because they've been able to get the entire world. But you know, the patterns of interacting on Facebook among like people at Harvard where it started are probably very different from the people who are like signing into Facebook now in China or some other country. And so the heterogeneity in the data generating process as the data set got huge would call for a model that has a whole lot of heterogeneity in it, probably a multi-level model. So it's true that if you just do like ordinary least squares, no interaction terms, like no heterogeneity in the data generating process on a data set with like 2 billion observations, yes, you have like pretty much no uncertainty about the parameters, given that that's the right model. But you're faced with the question, is that the right model? And even if it sort of like could be the right model, in order for it to be like a really good model, you would probably want to start to incorporate different heterogeneity in the data generating process, different countries, different minority groups of people within those countries behaving differently in the way that they are generating the data, and then you end up with a model that is a lot more complicated. Maybe it has thousands or millions of parameters in it. And when you get to that, then we're no longer having like negligible uncertainty about the millionth parameter. we might have like still enough that you would want to keep in account of it. And so these big data sets offer opportunity to do really rich models, but a lot of the frequentist things and a lot of the supervised learning stuff that just kind of adds a penalization term onto a frequentist procedure doesn't really take full advantage of the opportunity that the data set provides if you could do like, you know, a really nice model with Stan with something like that. So the penalty functions being used in supervised learning often make for poor priors. I linked to a blog post by Dan Simpson about that because they weren't really intended to be priors. What they were intended to do is shift the mode away from like the maximum likelihood estimator more toward the prior beliefs, but not really intended to capture your full uncertainty about the parameters before you see the data. And then there's a lot of, you know, you could do this in RStanArm. You can just do prior equal lasso, and it will do the blue curve here. And so it's relatively easy to get like the whole posterior if you wanted to, even though it's kind of a weird choice of priors. But a lot of the supervised learning people not doing MCMC, they're just doing optimization to get that posterior mode and ignoring all the uncertainty that they should be keeping track of, which is really what I think is the hallmark of the Bayesian approach. And if you go back to this decision, well, in order to decide what model predicts best, you need to split it up into like 75% training data, 25% testing data. Well, if you're taking the Bayesian approach, you're like, I would really like to condition on that extra 25% of data in order to get posterior inference on my parameters that had less variance. And so by holding that out, not conditioning on it, I get a posterior distribution that's more diffuse. And if you take the supervised learning approach, you might be like, well, that doesn't really matter. We're going to be ignoring all the uncertainty about it anyway. But if you take the Bayesian approach, you might say, well, splitting it into training and testing is costly because I'm not utilizing all the information that I have. How could I still make conclusions about what model predicts best, but without necessarily paying the cost of having to not condition on a big chunk of my data and thereby getting more variance in my posterior distribution. And of course, as we've seen, the Bayesian approach readily allows you to make predictions. There's a little bit of a myth that I encounter a lot, which is like, if you're doing a randomized experiment, then you should do design-based inference. And if you have a survey, you should do frequentist inference. And if you're worried not about the parameters, but about the predictions of future data, then you do machine learning things. But the Bayesian approach is actually general enough to encompass all of those. And certainly you can get predictions from a Bayesian model with the posterior predictive distribution. And it's actually better because instead of getting a single prediction for one held out point in like the testing set as to what its outcome would be, you get S predictions for each held out data point. And so your predictions have uncertainty that comes from the fact that you're uncertain about the parameters. And even if you knew the parameters, there's sort of fundamental uncertainty in terms of measurement error or randomness in your subjects, like babies taking IQ tests or whatever, that is going to, you know, generate noise in the outcomes you observe in the testing data. So being able to predict with uncertainty as opposed to just predicting with a single point, I think is one of the main advantages of the Bayesian approach to prediction that a lot of people don't fully internalize if they're not sort of thinking about things from a Bayesian perspective in the first place. There's also predictive distribution for frequentist, but it's very weird. So we're not even going to talk about it. But one of the things, so the reason to like split this up into training and testing is that they're worried about overfitting, estimating a model that's too complicated and overfitting in the training data and thereby obtaining predictions that in the testing data that are not as good as could be achieved by a simpler model. And so there's a big concern in the supervised learning literature about overfitting and thereby getting poor predictions of future data. And so if you go back to this model that we estimated with StanLM for diamonds, it had like 25 coefficients in it. And you might wonder, are we overfitting this data set that we have, even though the data set we have is relatively large? And so we estimate that model, same as we did before. We call posterior predict. And this, with like draws, is 1,000 if we're running out of RAM and we can only do a subset of our posterior draws. And so this output PPD for posterior predictive distribution is going to be an S by N matrix. And so each column is S predictions for what that outcome will be, given the price of the carat and the size and the clarity or whatever of the diamond you're predicting. So you can think about it, each column this is by distribution of prediction for those X's. Or each row, you can think of that as my prediction for like what a whole sample of data would look like. And that's part of what's going on in the homework for Thursday, different ways of looking at that posterior predictive distribution. But one thing that you can do, even though you weren't asked to yet on the homework, is to calculate the quantiles of the posterior predictive distribution column-wise, like using the apply function. And so we can get the lower 25% quantile and the 75% quantile for each of those n columns, which is like 54,000 in this case. And then we can evaluate on the data that we have. There was no splitting of training and testing in this situation. So, the log prices that we do observe, we can count up the proportion of times that the observed log price is between the 25th percentile and the 75th percentile of what our model predicts the log price should be, taking into account our uncertainty about the coefficients and the intercept and the standard deviation of the errors and all that. And it comes out to 53% of the observations, of the n observations, fall inside our 50% central interval. And you might say, well, wouldn't it be better if like 100% of the observations fell in the 50% interval? And the answer to that question is no. If you define a 50% interval, it should have a 50% probability of including the random variable that is ostensibly predicting. And so what we would want here is for 50% of the observations to fall in a 50% predictive interval. In fact, it's 53%. So we're overfitting the existing data that we condition on by a little bit. Not that much, but a little bit. And so if we were to do this on like actual future data, we might see like a 50% interval only including like 46, 47% of future price data. And you might say, well, I could live with 3% overfitting. And you probably can. And that is, I think, one of the most important things to recognize is that the supervised learning people say, okay, split it in training and testing because you don't want to overfit and estimate an overly complex model, predicts poorly future data, all that, and sort of giving the impression, the distinct impression, that the root of overfitting is sort of the lack of splitting into training and testing, not holding out some 25% of the observations to evaluate the model fit on that were not used to train the model or to otherwise attain the parameter estimate. And that's true, but it's only, in my opinion, a small component of the phenomenon of overfitting. The big component of the phenomenon of overfitting is the choice that the supervised learning people make and the choice that the frequentist people make of taking your one mode as the truth when making predictions. And so if you just take this one point that is what optimizes your objective function on the data that you train it on, the predictions that stem from that one point are going to be overly sensitive to the data that was used to estimate those things. So if we do like maximum likelihood, and it's almost 2 or whatever, maximum likelihood is defined as the value of beta that makes the sample of data that you have the most likely to appear from the population. And so it's sort of by definition overly influenced by the particular sample of data that was used to estimate it, not calibrated for future data. And similarly, if you penalize, but that's a little bit better because it gets you closer to the posterior mean. And so the fundamental solution to the overfitting thing is to not go to a mode, stop, and use that one point, but to make predictions off the whole blue curve, not just one point. And now your predictions have the appropriate amount of uncertainty in them. And as a result, the predictive performance in the data that you conditioned on tends to be fairly similar to the predictive performance in actual future data if you're keeping up with the uncertainty and propagating it through to the predictions. Now, you'll get a little bit of the phenomenon that the supervised learning people were talking about if you don't split into training and testing. But this, I would say, is a fairly typical occurrence where you see like 2-3% overfit if you posterior predict the data that you just used to obtain the posterior distribution on. And so that's a little bit of a thing, but it's mostly taken care of if you just propagate your uncertainty through. Yes, Keith?
How does cross-validation?
We're going to talk about that. But does everybody understand what I was getting at there? That really, in my opinion, the big part of the overfitting phenomenon is just using the one optimal mode that you obtained in the training data and making all your predictions based on that one point, as opposed to putting like 5,000 draws from the blue curve through the prediction and now getting that uncertainty interval.
Would that be the same case if you use like a model that's not?
Yes. We're going to do a less complicated model next.
So that means like the mode is true regardless of the count.
Right. Every model, whether it's complex or not, is going to have a mode. But from a Bayesian perspective, the posterior mode is really a red herring. It's not any more important than any other point in your posterior distribution. It's less useful than the posterior mean. It's less useful than the posterior median, because the posterior mean and median, they're one point, but they're sort of reflective of all points. Whereas the posterior mode is literally just like the one that is most likely, but you have to take into account how much, curvature and like the whole distribution of it. And so a less complicated model like this one, I took out the interaction terms and did it again. So my overfitting is now down a little bit to 52.7, so 2.7%. But then the question, okay, yeah, this one overfits less. But is that reason for us to say, well, the simpler model would be better? We should use it rather than the more complex model that had interaction terms between caret and the dimensions of the diamond. Catherine.
Question. So you got 53% and you said the probability at 0.25, 0.75. Is it the case that like the probability adds up to 1, right? So it means like if we say it to be below, then that's going to be underfitted.
Right. So 25% below the lower bound, 50% in the middle, and 25% above the upper bound. Now, I could have chosen this differently. I could have made an 80% interval, in which case I would want 80% of the actual observations to fall in their respective 80% predictive intervals.
So therefore, even though you conclude from this interval that this is overfitting, it could be the case that it's no longer overfitting if you choose a different interval, right?
Right. If I got in like 12%, that would indicate my model is very much underfitting.
Yeah.
And that would be bad too. Probably worse.
Right. So,
but anyway, you should know. You can tell.
so I just guess like, because we're only looking at this interval and moderating the model according to this interval, if we change a different interval with a modified model, it could still have like other issues, right?
Yes, definitely.
Yeah,
And
okay.
you want to do apples to orange comparisons here. So it doesn't make sense to compare like a 50% interval of one model to an 80% interval of another, or a 50% interval for one dependent variable and a 50% interval for another dependent variable. Like that isn't a valid comparison. But different models, same data, same size or same percentage in the intervals, you can do things like this. But anyway, a model can overfit part of the data set and underfit another part of the data set simultaneously. So just because this one overfits a little bit more or a little bit less doesn't necessarily mean it's like one is that much better or worse. We need a comprehensive way of evaluating the predictive performance of the model. And for Bayesians, it's really the utility function for prediction. The best one that you can use is the logarithm of the predictive density of future data. Now, there's been a lot of efforts to try to come up with like a more appropriate utility function. And it's hard to come up with something that's better than this, and easy to come up with stuff that's worse, like ROC curves or a lot of other stuff that you see out there on the internet. So just start with, really think about your utility function for predictions as the logarithm of the predictive density function. It's sort of the negative of entropy. Remember, we defined entropy as like the expectation of the negative logarithm of some PDF or PMF. And so entropy sort of says like, how uniform is this distribution? But when we're talking about predictions, we don't want to say like, oh, uniform prediction over the whole real number line. That's basically just saying we predicted this outcome is going to be a real number. That's not useful. What we really want for predictions is like the opposite of entropy. We want highly concentrated distributions on what the future outcomes really turn out to be. And so you have the logarithm of this predicted density, and you can take the expectation of that logarithm of the predicted density and choose the model that maximizes expected utility. Remembering, okay, so if here we have this density for n future data points, n plus 1, n plus 2, up to 2n, etc., conditional on the past n data points. You might say, well, how do we get at that distribution, the conditional distribution of the future given the past? And remember, this is what I call the Bayesian hokey pokey, where you introduce the parameters, multiply them by a posterior distribution of the parameters given the data, and then integrate the parameters out in order to get the distribution of future given the past. And then you can take the logarithm of that, and then you can take the expectation over the future to evaluate these models. Now, we don't have the future data yet, and so we have to take some steps to estimate this quantity. But fundamentally, this is what we are talking about from a Bayesian perspective when we say, okay, what model maximizes our expected utility, where our utility function is the logarithm of the predictive density of future data. And as Key alluded to, we can use cross-validation for that, although it's rather different from what supervised learning people do when they do cross-validation in an important respect, which we'll talk about now. So we can obtain draws using STAN from a posterior distribution that has whatever PDF we want, as long as it's differentiable. We can take those draws from the posterior distribution, stick them into our predictive function, so condition on each of our S draws get back S predictions for each of the future observations with the future X's. Now, imagine, suppose you omit the ith observation from the data set. So you leave out the ith observation. I can be any number between 1 and n. And you get the posterior distribution conditional on your n minus 1 data points. And then you use that posterior distribution to predict the outcome for the one observation that you left out. That process is, not necessarily doing the Bayesian version of it, but that process of leaving one observation out, doing something to estimate, and then predicting the one left out observation is known as leave one out cross-validation. Now, you don't see a lot of people doing leave one out cross-validation because it's very expensive. There's n observations, each of which you can leave one of them out and then re-estimate the thing and re-predict the thing. But it is a really good way to get predictive performance of a model. But what you'll usually see people do is more of a shortcut of like k-fold cross-validation, where they'll leave out like 10% and then estimate the model and then predict the 10% that was left out. Do that 10 times, one for each of the 10% segments that you could leave out. And that's fine as well, but the sort of limit of k-fold cross-validation as k gets to n is leave one out cross-validation. And that is sort of conceptually a really good way to estimate this expected log utility, or expected log predicted distribution, or expected utility, is by doing leave one out cross-validation. It's just extraordinarily expensive because you would have to re-estimate your model n times, once for each of the n observations that you leave out. And if you're doing MCMC, then that's going to be like very expensive and probably pretty unreliable, because you have like 50,000 observations, the Markov chains are going to go wrong for like at least one of the ones where you leave it out and then predict with the rest. And so it's not a very attractive route in practice, even though in theory it gets at the quantity that we want to get at. And so what Aki and some of his co-authors have been able to do is to come up with a procedure that allows you to estimate that thing without incurring the same computational and time cost, using what's known as importance sampling, or Pareto smooth importance sampling. So if we have S draws from the entire posterior distribution, by entire posterior distribution, I mean conditioning on all n observations that we have. The question that is talked about in the reading is like, how could we reweight those posterior draws for conditional on the entire data to be a posterior distribution conditional on n minus 1 of the data points? So how can we reweight our posterior distribution to decondition on one of the points that we originally conditioned on? And how can we do that for each of the endpoints that we have in our data set? And it turns out that is readily possible using what's known as importance sampling. So we can get from just estimating the posterior distribution once, n ways of reweighting to get n posterior distributions that would leave out one observation. And the weights used to obtain that involve the likelihood function for each observation evaluated over the entire posterior distribution. So if I have S draws from the posterior distribution, I want to go through my observations one by one and evaluate the contribution of the ith observation to the likelihood function across the S draws from my posterior distribution. in order to obtain the weights I need to use in order to re-weight my thing in order to get estimates of the leave one out cross-validation predictive performance. And all this happens automatically, so you don't need to memorize these formulas or anything like that, but just remember that the weights are related to the contribution of the ith observation to the log likelihood viewed as a function of the parameters. And that's, in principle, a valid procedure, this reweighting thing, but the weights can be really noisy for any sort of finite choice of S. So is there a way that we can obtain weights that have less noise without introducing very much bias? And the solution to that problem is to fit a so-called generalized Pareto distribution to the tail of the weights. The generalized Pareto distribution has this PDF here. So just deterministically with like optimization or whatever, fit Pareto distribution to some proportion of the right tail of the weights, which have a lot of noise in it, and substitute the predictions, point predictions implied from that generalized Pareto model for the actual weights. And this reduces a lot of the bias, or a lot of the variance in the weights, with only introducing a tiny amount of bias that tends to go away if you have a moderate sized n. And so that works great if your estimate of the shape parameter of this generalized Pareto distribution is not too large. So if it's greater than 1, then the sort of expectation of the generalized Pareto distribution doesn't exist, and this reweighting procedure is not valid. If it's greater than like 0.7, if you maybe have a 1 or 2 of those, it's not so bad. But if you have several of those, the convergence of this estimator to the truth is rather slow as things increase. So that's not great as well. But if it's below 0.7, particularly if it's below 0.5, then you're in the clear. And this is all estimated for you, and so you'll get warning messages if you're in a situation where the assumptions of this procedure are not being met. And the assumption of this procedure is essentially that you could leave one observation out of your data set, and it wouldn't have too big an effect on your posterior estimates. If leaving out the 17th observation would have too big an effect on the posterior distribution for this reweighting thing with S draws to compensate for, then what you should do and what it'll tell you to do is actually leave out the 17th observation, re-estimate the thing again, predict, and that will be your leave one out predicted performance for that observation. But you can use the Pareto smooth thing for the other n-1 observations and where the assumptions are satisfied, and that's going to be fine. So sometimes you do have to refit your model like a couple times for the problematic observations, but you don't have to refit your model n times because the Pareto smoothing process is adequate for most of your observations if you're fitting like a reasonable model in the first place. And so we can use this in order to get at this expected log predicted density, which we can use to then say this model is expected to predict future data better than that model, which is a bit different from saying this model is true and the other one is not. We'll get into that more next week, but we can say this model is expected to predict future data better than another model. And as an example of that, we have some data. Again, it comes from the reading from last week, the Gelman-Hill Vitari forthcoming book. This is national election study data on American presidential elections. So here we're going to be looking at the election in the year 2000 between Al Gore and George W. Bush. So we'll just take that subset of data. We want to treat the income variable as a factor rather than as continuous. And I want to divide the ages by 10 in order to get a more reasonable interpretation of the coefficient. Some of you, I think, ran into problems with this on the homework, where the units of your predictors are in like units of 1. And so you're trying to say, okay, how much does like 1 poke increase the probability of me having more followers or something like that, when that has like such a small effect that it looks like it's 0 when you estimate the thing and print it out and stand GLM. And so you scale your variables into more reasonable units. So we're not interested in like a 1-year difference between people and their voting behavior, but maybe like 10 years. That would have a big enough effect that we could actually like hope to capture it. And so I estimate a logit model for do you vote for George W. Bush instead of Al Gore, using the respondent's age, the square of their age, so there's a polynomial effect there, their income category and whether they're white with just a logit model. And then I call the LU function, which does this leave one out cross-validation business. And I get expected log predictive density from leave one out cross-validation, negative 575. Now that number has no meaning in absolute terms. It's only relevant when you compare it to another model, and we can say this one has a bigger expected log predictive density than some other model. But if there had been any problems in terms of the assumptions like not being met, I would have gotten warning messages all over the place about Pareto K hats too big, you know, leave stuff out, etc. In this case, it didn't happen, so we're in the clear. I can estimate another model, and we'll get into this more because we're running out of time today, where instead of saying the effect of age on the probability or the log odds of voting is quadratic, we can say it's any smooth function, and then approximate that smooth function by the sum of a number of basis functions, each of which has a coefficient. And so this smooth model that I estimate with stan GAM4, pretty much everything is the same, except rather saying a quadratic function of age, I just say S age, saying estimate me some smooth function of age. This is a much more complicated model. It's going to be estimating a lot more parameters to capture this sort of arbitrary nonlinear but smooth function of age that I'm saying is related to the log odds of voting for George W. Bush rather than Al Gore. And I can estimate that model. I might have to bump up the adapt delta in order to make the divergences go away. But if I look at the plot of my Pareto hats, they're all well below 0.5. So I can leave out any observation I want. It's only going to have a small effect on the posterior distribution. And that small effect I can account for with this reweighting process in terms of important sampling weights. And then I can call LU on those things and just kind of eyeball the difference. Or I can call the compare underscore models function, which will give me the difference in expected log predicted density. And as it says here, negative values of it favor the first model, positive values favor the second. And so I got expected log predictive density difference of 1.4, so favoring the expected second model by 1.4. And that has an estimated standard error of 0.4. So there's some reason to prefer this second model in terms of its expected ability to predict voting in subsequent elections, like the George Bush, John Kerry election in 2004 or whatever. So maybe the model with the smooth age term is better than the model with the quadratic age term, at least according to this criteria. And that's true even though there doesn't seem to have been a large effect of age on the probability of voting for Bush in that particular election, which we can plot with the plot nonlinear function, spits out a GG plot of the estimated smooth but nonlinear function, which actually turned out to be pretty close to linear. But there's a lot of uncertainty around it, particularly at the edges where we don't have like a lot of 90-year-old people in the data set, and also not a whole lot of 18-year-olds in the data set. So we have more uncertainty as to what is the true sensitivity of log odds of voting to age in those. But even in where we have like more 45-year-olds or whatever, and the interval is narrower, it's still sort of a lot of uncertainty, and the overall slope to it is still pretty close to zero. So it doesn't seem as if age had maybe that much of an effect in that election. But the ELPD comparison is telling us that this model is expected to predict the 2004 election, let's say, better than the quadratic model that I estimated. And we can use this blue and ELPD concept to compare any two models on the same outcome. But you have to also have the same N. So those are some of the restrictions. There's some assumptions that go into it, but if those assumptions get invalidated, you'll get warnings. And the warnings will basically say, like, do this, and we'll actually leave out a couple observations, re-estimate the model, and then get valid estimates of this ELPD thing, which can be used to compare different models. Okay, out of time for today. Pick it up on Thursday, talk more about visualizing prior predictive distributions, posterior predictive distributions, other things you can do to compare different models. We'll talk about the homework, but still all using like RStanArm and other R packages that have all these functions and calculations built in. Let's see you then.
也是时间。